Hello, my name is Parzival Borlinghaus, and together with Stephan Huber, I'm presenting our explorative work on the automation of affinity diagrams.
Affinity diagrams are a method commonly used in user research to cluster qualitative data. Observations and user statements are written on individual nodes and hierarchically clustered bottom-up. The resulting diagram builds the bridge to design, as Holzblatt and Bayer put it, and allow to derive insights about user needs as well as inspire design ideas. However, manually creating the affinity diagram is extremely time-consuming and can keep a team busy over several days. So our research question was how we can make affinity diagramming more efficient without losing its benefits for the design process. That is, allowing the designer to dive into the data and learn about the user's need. In this work, we restricted clustering to the lowest level of the hierarchy, where the clustering process starts and most time is spent. Higher level headings should be generated by designers themselves or be addressed in future work.
I will use the next couple of slides to introduce you the data we used and the models that we took into account. Affinity diagrams often consist of hundreds, sometimes thousands of affinity nodes. Affinity nodes share some simplifying characteristics, such as their similar length, acceptable spelling, and rare usage of negation. Affinity nodes are written in story language and from the user's point of view. Exemplaric nodes from the bicycle projects are "I'm annoyed when the police stop me without a reason" and "I like to ride through the park because there's not much going on and I'm faster." Since this is only a 10-minute talk, I cannot go too much into detail. However, I refer to the paper where all the models are briefly explained. The models were compiled with diversity in mind. Some of the models utilize modern context predicting approaches, some are rather mathematical and are based on the decomposition of word count matrices. Later models must be trained and make use of training data such as the Wikipedia corpus. All of them can be used to find document embeddings in the semantic vector space. That is a space where similar documents are represented by similar vectors. Please note that similarity can be measured in multiple ways. Due to the high dimensionality, 300 and more are common, the usage of cosine similarity is widespread. The most suitable model was determined by a human similarity task. 10 native speakers labeled about 300 sentence pairs from an open-ended survey for relatedness in meaning. A model that is suitable to auto-generate affinity diagrams should be able to reflect the human sense of semantic relatedness. The degree of similarity was measured with Spearman's rank correlation. FastText turned out to be the best performing model with a rank correlation of 0.44. FastText was published by Boyanovsky and colleagues and falls in the class of context predicting semantic models. As the name suggests, it's fast to train since it processes subwords. Subwords model the internal structure of words like prefixes and suffixes, which is beneficial to morphologically rich languages like German. Boyanovsky and colleagues choose all subwords of size 3 to 6 that occur in the corpus. Another beneficial side effect of subwords is the unlikeliness of out-of-vocabulary errors. The subwords embeddings are subsequently summed and form the document's embedding. However, FastText is not capable of word sense disambiguation. That is, FastText is unable to distinguish between words of the same spelling but different meanings. This slide shows the performance of FastText in the wild. Applying FastText to 6 affinity diagrams and comparing the results to human-generated counterparts lead to promising results. The clusters were compared using overlap and Jacquard indices. This resulted in an average overlap index of about 0.7 and an averaged Jacquard index of 0.3. For comparison, 2 random affinity diagrams with 250 nodes and 69 clusters result in a Jacquard index of less than 0.008. We can conclude that FastText is in principle a good choice for the automation of affinity diagrams. We therefore conducted a study to determine the helpfulness of FastText pre-clustered affinity diagrams in real-world applications.
We set up an evaluation study to test whether algorithmically supported affinity diagramming is more efficient without losing its value for the design process. In the first part, we focused on efficiency and hypothesized that design teams working with pre-clustered affinity nodes would be faster in building an affinity diagram than design teams with randomized affinity nodes. In the second part, we interviewed the design teams while they explored and evaluated a FastText-generated diagram of nodes they were familiar with. Finally, experts rated the quality of diagrams that design teams had clustered in the first part of the study, compared to a reference version created by a design team without any time limit and a reference version entirely clustered by FastText. Opposing our expectations, the group working with random nodes progressed faster without a significant difference in workload. A reason for this may be that the teams in the FastText condition spent much of their time discussing if the suggested groups were a good match or not, while the teams in the random condition just started from scratch. Key insights from the second part of our study were that participants suspected a change of task that came with the algorithmic support. Instead of thinking with their hands while manually clustering data, they were afraid that they had to merely correct the already pre-clustered FastText output of seemingly ready affinity diagrams with too much information at once. They saw a potential benefit when working with large amounts of data, especially if they were familiar with the data already. Experts graded the reference version of the affinity diagram best, and the entirely FastText-generated affinity diagram worst. They judged the FastText-clustered version as seemingly following a mere sorting by similar words with a lack of semantic. At the end of the study, we disclosed the origin of the diagrams to the experts. One expert remarked that they had experienced similar quality from student design teams before and would have expected from the computer to do better. Summarizing our contributions, we examined 7 text mining models and found FastText to be most appropriate for pre-clustering short qualitative nodes. Even though there was no measurable objective benefit, algorithmic support has much potential and the concept was generally accepted by participants in our studies. For future work, we recommend to shift the point of algorithmic support in the process, so that designers do not have to rearrange pre-clustered data, but are supported as they cluster the data themselves. This could be achieved, for example, by highlighting nodes that could match the content of a cluster the designer is momentarily working on. Conveying confidence of suggestions would be a great challenge here to promote the designer's decision-making process and acceptance of the algorithmic support. Thank you very much for your attention in this short overview. You will find more details in the paper, and now we are happy to take your questions.